ones are not necessarily exactly along those lines, but it would be fine, I think, if those students heard this as well. Why do this set of lectures? Well, I really want to advertise, and I would like to make this easy for other people to use. So it's a funny thing. You're in graduate school and you're writing your code, and you're knocking yourself out, and you're worried all the time. But what's going to happen is you're going to write your paper and publish some results, and then someone else is going to go through and they're going to code up your method and then show somehow that you were inefficient or you got a slight bug, and then you'll be embarrassed. That is not the problem. The problem is that no one will ever implement your algorithm, and it will be lost in time, and it makes no impact. So how do you get away with, how do you avoid that fate? How do you make an impact? Well, I'm convinced now that the way to do this is to write code that you distribute and that you encourage people to use. And now this is a hard problem, because if it's a complicated code, we'll give up easy. I give up easy. So what can you do? Well, it's better if you have a simple idea. It's also better if you use something like MATLAB. So what I like to do, while I'm doing these lectures, I've got a couple codes ready to go today, and in the weeks and months that follow, if I get a bit of feedback from you guys, is to have a set of codes available, at least at my website, and perhaps through the Newton Institute website as well. But a larger scale goal might be the following. There are a number of groups who do very good numerical work on simulating water waves, and everyone's got their own code. And I'm very afraid to implement these other codes. Wouldn't it be nice if there was some sort of repository of perhaps simple versions of the code? Now, I understand, many times you need to do a gigantic simulation. It's got to run on a parallel computer. It's going to be, it needs to be sophisticated. But at least a simplified version that, that other experts who use a different method could use, or someone who's not particularly numerical could use, at least to get an idea of what's going on. And so perhaps that could be a larger goal. So with that in mind, I want to tell you about my method. So where does my method come from? Well, my method was taught to me, at least the first parts of it, by my advisor, Walter Craig, and we'll call it the method of operator expansions in just a moment. But there are a number of other approaches in this vein which have the same philosophy, and they get different names as the years go on. And as you start working with engineers, it becomes apparent that you need an acronym if you're going to be an engineer, and you can't just have some letters that come together and don't make any sort of sense whatsoever. But it's hard to come up with a good acronym. Many people, it seems, seem to spend more time on the acronym than they do on implementing the code. We did not do this. So we eventually came up with HOPS, High Order Perturbation of Surfaces Methods. So that's the explanation for the title. There are a number of collaborators on this. The ones I list are just the ones who've actually designed the algorithms with me. There's others, like Philippe Goyen. We've used the methods to study water waves. But paramount among these are, well, Walter Craig was the one who got me started on all of this. I've thought about these methods for a long, long time with Fernando Reitig in the context of electromagnetic scattering, but related problem, who's in Minnesota. Ben Akers, who's going to be working with me to present these lectures, who's now at the Air Force Institute of Technology. And then Allison Malcolm, Jay Shen, Purdue, Nilima, again for electromagnetics at Simon Fraser, and then a number of students. All of my students have used methods along these lines, but these ones in particular have been the ones who've been working on the design of these algorithms. So Mark, Carlo, Zeng, and Venu. Many people have been very kind with their money over the years, and these are the most recent ones, the NSF and Department of Energy. References. There are many, many references, but here are the ones that I always start with. So there's this fellow Milder who works for a company, or at least he worked for a company in the 90s called Arete Associates in Southern California, and he had in mind problems in electromagnetic scattering. And so he published a line of papers beginning in 91, 92 on the method that I'll call operator expansions. Craig and Sulem had this paper that was very influential to me personally, but I think also to water waves community in '93, where they talk about how to simulate water waves numerically with a HOPS scheme, the operator expansions method, and it's very, very similar in spirit to what Milder did, different context. Bruno and Reitek, so Oscar Bruno is at Caltech in applied math, were working on electromagnetics problems, and they used a slightly different approach to all of this, the method of field expansions. And in a series of 3 papers, they told you how to do this in rectangular coordinates for 2D and 3D, and they have some really nice results. And then after I left graduate school, I went to Minnesota, and I found Fernando, and we started collaborating. And we saw, and you'll see it in the numerics that I show you later, and then I'll give you a code. You can verify it yourself, and you can break these things as hard as you like. We noticed that there was a problem with these high-order perturbation of surfaces methods, and we attempted a fix. And so that was this line of research in these 3 papers. And then from there, it sort of took off, and much of my career has been built on these numerical schemes and then applying them to physical problems. So then you can go to my webpage, and you can bore yourself to tears reading a number of different papers on these lines. All right, so what am I talking about? Well, in theory, it's on the broad topic of numerical solution of partial differential equations, a vast and enormous field. Every year at UIC, we advertise for positions, which always turn into 1 position, and we get many, many applicants, thousands. A huge fraction of those are in PDEs with a numerical solution of PDEs, huge field, as you all know. And now with the advent of the modern computer, what you've been able to do is you've been able to implement all of these ideas that you had throughout the centuries, probably going back to Newton, and see the results. And we're all familiar with the classical categorization of all these different methods. The finite difference methods were perhaps the first ones to come along because they are the first thing you think of if you know calculus. Somehow methods based on difference quotients, letting the size of the difference go to 0, and then proceeding from there. A very clever idea, which came from the engineers, and which has been very, it steered the entire field. And much of the field of pure partial differential equations was the advent of the finite element method, which took the PDE and didn't take it at face value, but rather formulated it in a new way, weakly. So it turned out you got all sorts of great advantages by making this weak formulation. And now, this is a number of different AMS mathematical classifications, discontinuous and continuous finite element methods. So as you all know, the idea is that you seek a solution in a function space, and to make it finite dimensional, you say, well, the whole function space is too much. I'm going to look at a finite dimensional subset of this function space, and then I'm going to constrain or enforce conditions, a finite number of conditions, to recover the coefficients of the expansion of my approximate solution to this finite dimensional function space. And so the question becomes, what are the basis functions, and then how do you make the equations that you want to satisfy? And that distinguishes among many of these different methods. Do you use polynomials, low order? Do you use high order? Do you use things that look like complex exponentials? Which polynomials do you use? And so on and so forth. But now, if you've got special structure in your partial differential equation, well, you should take advantage of that whenever possible. That will save you vast amounts of time and huge amounts of potential error. And so if, as you have in the water wave problem, you've got huge swaths of the domain which are homogeneous, then if you can get away with it, you should not discretize the homogeneous part. You should only discretize the part where you have rapid changes from one area to the next. And so, of course, in the water wave problem, you've got the body of water. And if you can get away with it, you should not discretize inside the body of water. You should discretize just at the boundaries, the interface between the fluid in the air and the interface between the fluid in the bottom, and then whatever lateral boundary conditions you put in. And perhaps if you're lucky, drop out. So if you take advantage of this, then you can realize huge savings. And this is the idea behind binary integral and boundary element methods. This is just some of the methods. These are probably most of them, but there are any number of variants on these things. So I don't want to do any of this. I'm going to do something a little bit different. So to put it into context, these high-order perturbation of surfaces methods, HOPS schemes, will not work well for all problems. And in fact, they will work quite poorly for most problems. But for the class of problems that we're interested in, it will work very, very well. So what do you need in order for this to be an appropriate scheme? Well, you need some sort of domain which is piecewise homogeneous, where it's advantageous to have unknowns posed at the interfaces between these layers. And then it's best if the shapes of the layers are nice and smooth. It's not a problem for water waves, because, for instance, if you look at traveling wave solutions, you have to work incredibly hard to get anything that's anything but analytic. You have to go to the very most extreme wave before you see something with something that looks like a corner. Otherwise, the surface is fantastic. Happily, there are many of these problems. Free surface fluid mechanics is a problem that we all know. Acoustic waves propagating in a piecewise constant density media, like waves propagating in the Earth. Electromagnetic waves interacting with grating structures, which is something I've thought about quite a bit. Elastic waves, and so on and so forth. You find yourself in such a configuration, and if you can devise one of these HOPS methods, then you'll find a number of advantages fall into your lap. A number of very nice features. One of which is high accuracy. These are highly efficient methods. As you increase the number of unknowns, as you increase the number of degrees of freedom, typically your rate of decay is faster than any polynomial, along the lines of exponential convergence. If you're clever, you can make the method very, very fast. Okay, so since you've already taken a volumetric problem and replaced it with one just at the surfaces, you've already got a reduced number of unknowns. But many times you can appeal to fast transforms, fast Fourier transforms, so that the matrix, how does it always work out with a linear PDE? You always have to invert a matrix. AX is equal to B. Can you invert A very, very quickly? Well, if you use the right unknowns, and if you use the right conditions, then you can invert that matrix in potentially n log n time, using the FFT algorithm or some sort of variant. And then the method, most of the time, is quite robust. You can always try and break a code, and these codes can be broken. But there are fixes. Fernando and I have thought a little bit about that. But for the most part, these deliver results which are pretty reliable. And Philippe has done this, and I've done this, and many others have used these, Walter and Catherine, to deliver highly accurate solutions to the water wave problem. And now, as I said, the schemes are not good for everything. If you have an inhomogeneous domain, if you have an extreme geometry, bad corners, the methods are not going to work so well. Okay, so let's remember the water wave problem. To fix on a particular problem, let's consider the following. So you've got the free surface between water and air. We need to determine that, and that's going to be called eta of x and t. And now let's suppose that the water is deep and two-dimensional. That will make the derivations initially much easier. And then the idea, the really nice things about these HOPS approaches, is that putting in these additional complications, for the most part, usually, doesn't really complicate the derivations all that much. And when you code things up, you go from 2D to 3D, it's going to be a bigger computation. But somehow you just add a couple extra loops, and now you've got a 3D version of the code. So it's potential flow, Laplace's equation on this domain, y less than eta. You want the vertical velocity to go to 0 as y goes to minus infinity, and then you've got the kinematic condition and the Bernoulli condition. G is going to play the role of a shape in my talks. And so G tilde needs to be gravity, because after this slide, it goes away. The velocity is given by the gradient of potential. Eta is the air-water interface, and G tilde is the gravitational constant. I don't want to talk about water waves today. In fact, I'm going to leave that to then. I want to focus in on part of the matter in some sense. I mean, as you know, there's two parts to the water wave problem. There's the business of solving this Laplace equation, taking, as you'll see, Dirichlet data and producing normal derivatives. Why do you do it this way, or you have to do it with an integral equation based on a fundamental solution, so on and so forth. Then the other part, of course, is that you've got these nonlinear conditions with high derivatives at the interface. That's the second part of the matter. So this is the first part of the matter, this business of solving Laplace's equation. So let's focus in on that. So let's retain Laplace's equation below some shape, now here comes G, which I'm going to ignore the time dependence. So you can imagine, if you're going to simulate the water wave problem, what you would do is you would go from one time step to the next. How do you get to the next time step? Well, if you use an implicit scheme, you use information at the previous time step, where the interface shape is frozen temporarily. So you can think of eta as being temporarily fixed. Just need to be able to solve Laplace's equation on this complicated domain, which is temporarily fixed. Its boundary condition is y goes to minus infinity, and then if I specify for you Dirichlet data at the top, and then some sort of lateral boundary conditions, to make it easy, let's do periodic boundary conditions. And if you want to do conditions where you have decay at infinity, one idea is just to make the period very, very large. You can approximate that situation. This is the operator, as Walter said yesterday, that ties everything together, that allows you to make a surface statement of the water wave problem. This is one way to make a surface statement of the water wave problem. It's a so-called Dirichlet-Neumann operator, or Dirichlet to Neumann map, or DTN map, or if you're in electromagnetics, the Steklov-Poincaré operator. And so what you do is you send this Dirichlet data Xi to Neumann data. Well, it's not the Neumann data. It's normal derivative, but not normalized normal derivative. And it's chosen for a number of reasons. First of all, because this is exactly what appears on the right-hand side of the kinematic equation. So if for no other reason, if you want to restate the water wave problem in terms of this Dirichlet to Neumann operator, it gets you off to a good start by making the very first equation very easy. Cannot do this forever. At some point, life has to get complicated, and it gets complicated with the Bernoulli condition. And part of the complication is that the Bernoulli condition is written for the velocity potential phi, and Zakharov tells us that phi is fine, but the conjugate variable is phi evaluated at the free surface. So you have to write down an evolution equation for c, which I'm calling phi evaluated at eta, because I'm Walter's student, and that's the notation that he uses. And so you have to chase around some chain rules a little bit. But after you're done chasing, you see that the evolution of the surface potential is this linear bit minus g tilde eta, which gives you that quadratic part at the very end of all of Walter's Hamiltonians, plus a nonlinear bit. And what does it look like? Well, you get a quotient part, 1 over 2, 1 plus d by dx eta squared. And then you get this nonlinear contribution, which includes powers of the x derivatives of eta, and c, and then powers of the Dirichlet to Neumann operator. If you're working in 3D, you get two other terms, which happen to cancel out here in 2D, but you can put those in. And so the point for the moment is that I'm going to focus for today on solving this boundary value problem, hence the title of the talk, and we just need to keep at the back of our minds that if we can do this well, then we can imagine that we could perhaps solve this problem well.
Can I ask a question, please?
Yes, of course you can.
Your operator big G on the
Yes.
previous slide. How would that work if you've got a very simple flow like flat surface with a uniform flow underneath it? Would that be included in the restrictions you put for
let's see. So the operator is all about taking Dirichlet data to Neumann data. So for the flat geometry, certainly you could produce that operator rather simply. For the business of the flow, I think what you need to do is you need to probably modify these equations here, wouldn't you? You need to put the flow term in somewhere.
So would it be, if you made that accommodation and just allowed a local horizontal flux, would that then make your operator very simple? Just as an illustration.
I think so. I think it would. I haven't thought about the detail, but I don't think that would be a big problem.
Okay, thank you. I don't want to interrupt anymore.
Yeah. And that's absolutely part of the objective. Hopefully, you write some very simple MATLAB scripts, solve very simple problems, and then you can imagine you could add in new things, and we could all see how easy or difficult it is to add in new bits. All right. So we need some boundary conditions, and apologies for how simple-minded some of these slides are. Let me go through them quickly. So we're going to impose the classical periodic boundary conditions. It gets us started. So the field itself, V, and the interface shape, G, are going to be L periodic, and let's make our lives even easier. Let's make L 2 pi. And so if that's the case, then you can express the interface, for instance, as a Fourier series, and this is a formula for the Fourier coefficients. We're going to focus on this boundary value problem, periodic in X, and then this Dirichlet condition at the top. Decay is y goes to minus infinity, and then we're solving Laplace's equation inside the domain y less than g. So let me talk about the field expansions method to begin with, because it gives you a one-line formula for the solution. So this traces its origins back a long, long way, at least to the work of Rayleigh, back at the turn of the previous century, and Rice, back in the 1950s, and this was in the context of acoustic wave scattering, but it's easily seen how you take that. I mean, in some sense, that's a harder partial differential equation to solve. It's just that the boundary conditions, in the end, there's no nonlinearity to that problem. And so engineers in the field of acoustics and electromagnetics have been using methods along these lines for a century. It's just that they never thought to take these expansions to high order for whatever reason. It's a bit of a complicated derivation. Do you really want to put it on a computer? The question is it worth it? And I'll argue that it is worth it. So it was the contribution of Bruno and Reitik to take this to high order and to see what you could gain by doing this. So they called the method of variation of boundaries. Well, when it became clear that there were many methods which were based on variation of boundaries, we needed to distinguish it from the other methods, and so the title of the paper is a little bit different. Fernando and I retitled it The Method of Field Expansions. Among the very small number of people who've read my papers, the name seems to have stuck. The key to the method is the following. Here is the solution to Laplace's equation if you are away from the interface. So the interface is irregular. Go down below the lowest point, and it's an elementary exercise from separation of variables, but that's what the solution looks like, up to constants. And so the idea is that if the interface is flat, then this solution is the solution all the way up to the interface. And that if you perturb the interface a little bit, then the solution shouldn't be too far away from this guy. And now the controversial part is, well, is this expansion still valid when you are inside the grooves, if you will? So if you are at some sort of point, so you've got this perturbed interface, if you're well below, no argument, that's the solution. But if you are near the interface, is this still what the solution looks like? This is the so-called Rayleigh hypothesis. So how do we try and make a bit more precise the notion of perturbation, small? Well, let's do it this way. let's suppose that the shape G is epsilon times f of x, where f is a function, say, of order 1. Then it turns out that the field V depends on epsilon now, because that's the shape of the domain. This is a regular perturbation expansion, and it depends analytically upon epsilon. You can expand it in a power series in epsilon, and it's going to converge strongly in a function space. And part of the idea of the lecture on Thursday that I'm going to give is to try and make the mathematics of that a bit more precise. If I keep at this pace, I'm never going to get there, which is usual for me. So let's suppose that this is all true and that we can make this expansion. What does that mean for our problem? So you take this expansion and you plug it into this problem. And now you try to equate at all the relevant perturbation orders. Decide what this means. So one way to discover what the covering equations are at each perturbation order is to differentiate n many times in epsilon and then evaluate at epsilon is equal to 0. And what you find is that most of the equations come through unscathed. So this condition, as y goes to minus infinity, is the same as it is for the full field at every perturbation order. The linear condition, that's not surprising. The periodicity at every perturbation order should be the same, linear condition. This here has always troubled me, and it's a source of problems for the method. So certainly if you take the Laplacian applied to that expansion, differentiate n many times with respect to epsilon and set epsilon is equal to 0, you will find the Laplacian of V is equal to 0. The key is, what domain is that satisfied on? Well, the domain shape depended on epsilon. What do you do? Well, I've always thought that you should differentiate that as well, but I'm not sure that's a well-defined operation. But you can certainly set epsilon equal to 0. And so this is the key to the method, is that you solve Laplace's equation on this simplified geometry at every perturbation order. And this is the key to the method, because this guy has the Rayleigh solution, which you can write down explicitly. And look how nice this is. First of all, V, the field, depends on two variables, x, the lateral, and y, the vertical. But you've got an expansion with only one index. You're not discretizing in y. You're only discretizing in x, because you're solving exactly in y. And now for periodic problems, what is your dream basis function? Well, it's the complex exponentials. For a function which is analytic, we know that the Fourier coefficients decay exponentially fast. And with a spectral method based on complex exponentials, what you do is you get the first n many right, and your first error comes because you've gotten wrong the n plus first guy, but that guy decays exponentially fast. So it's the best possible method. These are you couldn't design better basis functions for this problem. And they come out rather explicitly. And so, where's the complication? Yes?
I'm puzzled by, well, where you said you were puzzled, just as a thought experiment. Let's transform the domain to rectangle, just thought experiment. Then you would get...
That's lecture 3.
Yeah, but then just for the argument, that would mean that your Laplacian operator changes and you get epsilons in there. When you then would do the expansion, you get actually differences. Well, why then does this work? That's what puzzles me.
But that's exactly what
Because
we did
that's what you would think, that you would get some epsilon somewhere, because if you make it into a rectangle, right?
Right.
So that's puzzling.
So here, where does the epsilon occur?
In the first equation.
It appears in Q.
Well, that I
That's
agree
right.
with.
That's right.
But then you take y less
right.
than 0 for the Laplacian.
That's right. I've never discovered a great argument for why. But certainly you can take n many derivatives and then set epsilon equal to 0. And
No, with the equation I agree. With the domain, it's puzzling.
yeah. And so
Okay.
here's my fundamental complaint with this method. And it shows up later. Okay, I think this is about to go dark, right? Here's your problem domain.
You see, he hasn't specified Q, but all the trouble is in Q. You already sense it coming in the next slide, I guess.
Q will be complicated, but not too bad.
Okay.
Here is y is equal to 0, and here is y is equal to g of x. And you're solving Laplace's equation here. We're going to be concerned with quantities here at the interface. From the interface into the domain is a good way to go. From the interface outside the domain is a bad way to go. And now we're solving at each perturbative order here, which includes good points
And the bad one.
and bad points.
Yes.
So, yep,
But it works.
but it works
Okay.
up to a point.
Sure.
Yeah, because you said there was exponentially fast convergence.
That's right.
But is it also at the surface? Like at the surface? Not at the surface, of course.
So the only theorem that we can prove is after you do what we just discussed, you make a transformation first and then you expand.
Yeah.
If you do that, then your domain is, and this, I mean, you know this because we're all in free boundary problems. How do you get out of being a free boundary problem? You have to get onto some sort of domain which stays fixed, either through a transformation or reformulation in turn. So that was the way we got around it, and we can prove our theorems after the transformation. The problem with the transformation is that you now get terms over here. And so now you have to solve a volumetric problem again. You lose the benefits of solving a surface problem. Now, we can ameliorate this a little bit. We can make the domain you need to solve on very, very thin, but there's still a vertical discretization that needs to take place. And I'll talk about that on Thursday. What is Q? Well, what do you do? Here is V, and what did we say? V needed to be C at G, which was epsilon f. So now here you put in an epsilon f, here you put in an epsilon f, and now you have to expand this. And so what's the expansion? Well, at each n, when you pull this out, you're going to have Vn of x and 0, but there needs to be y derivatives to pull, I mean, it's Taylor's theorem. And there need to be powers of f that come out as well. And so that's why you get this. Okay. So at order n equals 0, this is the Kronecker delta, you get the xc. I'm being dishonest with you a little bit, because of course xc depends on epsilon as well. But never mind that. And now here are the terms from that second expansion, and you get some sort of, it's a convolution. It's a convolution in perturbation orders. But here's the point, is that these are v sub m's that you've already solved for. If you're at order 100, then you've solved for v sub 0 to v99, and those are all the guys you need to form q sub 100 to solve your problem. You have high powers of f, but they're divided by the factorial, so that's okay. That's very worrying. Many, many derivatives acting on Vm, and that will come back to haunt us. So this comes from this. Okay, so now we resolve to solve this problem. The solution to these three equations is this guy from the Rayleigh expansion. Possibly in the context of water waves, this has a different name. Probably Stokes. Or maybe even earlier. Lamb wrote it down. And Lamb was, his first edition was before Rayleigh. So. And so what do? You try and find these A's. So this is V order n, evaluated at x is equal to, y is equal to 0. And now these are the Fourier coefficients of q at order n. So what do you discover? Well, the q has a form that's not too complicated. At order 0, you get the Dirichlet data. And And then this is that convolution form. So it's v at order m, evaluated at 0. But before you evaluate at 0, you need to take all those y derivatives. And there's n minus m many of them. And because of the particular form that you had for the y dependence, it's going to turn out to be powers of absolute p. This is the sort of thing that turns up in these HOPS schemes for water waves. It's what turns out in, so if you studied Walter's slides carefully yesterday, you would have seen all these powers of absolute d, which is the Hilbert transform composed with an x derivative. This is going to give a Fourier multiplier. Each power of p looks like a first derivative. Classical first derivative would be ip. And so this is your one-line formula for the field expansions method. So what you want to recover, I'll argue, are these a and p's, coefficients of v sub n for each Fourier coefficient p. You get them in terms of the Fourier coefficients of the Dirichlet data, so that's good. And then you have to recursively recover these from previous orders. And how are they related from one order to the next? Well, you have to multiply by these powers of absolute value q, all right? And then you multiply by f, and this gives a classical convolution of the wave numbers p.
Can you remind me what f was?
F is the, okay, so the shape of the interface was little g, and we called that epsilon little f.
So it's the Fourier expansion of f.
That's right. Capital F sub m is little f to the m divided by m factorial. It's whatever comes out of Taylor's theorem.
Okay, sure.
So it's divided by m factorial. It gets very small as the power gets large. And now one thing that Bruno and Reitik noticed, used to their advantage, is that if f has a finite Fourier expansion, for instance, if it's a cosine, then a lot of this sum you don't need. So at order 1, you've got f to the first power. You only need to go from wave number -1 to +1. At order 2, -2 to +2. And so in fact, you only need to recover these p's for a very small subset of p's, and you only need to do a very small fraction of this convolution sum. So their algorithm was greatly accelerated compared to what I've coded up. What I do in my codes is I use the fact that multiply on the physical side, and then you FFT. Let's see, how's it go? Do a convolution with the FFTs. Move to the, from either physical space to Fourier space or vice versa, and then you multiply pointwise, and then you come back, and then you've done an FFT, or you've done this convolution. And so this is good. This was always Fernando's selling point about his codes, is it's a one-line formula. But now this doesn't give us what we want. It's fine to have the field everywhere inside the fluid, although we're a little bit worried about what happens exactly at the surface. But we wanted the Dirichlet de Neumann operator. Now, we've got Dirichlet data, so we've solved that problem. We would like to produce Neumann data. And so you need to add in a little extra something. And then this is my list of troubles. The FE recursions deliver the solution everywhere well inside the problem domain, away from the interface. But the question is this expansion valid at the boundary or near the boundary? If you assume that there's some sort of validity at the boundary, then what do we want? We want this Neumann data, the unnormalized normal derivative, dyv minus dy dxg times dy dxv, evaluated at the interface g. And so what do? Well, you take this form, you realize that it depends on epsilon, and then you plug in epsilon f, but you've also got to not evaluate v there, that would just recover the Dirichlet data. You got to take the y derivative and the x derivative, and then combine it in this particular way. That's this slide right here. And so, if you believe that, and if you believe my previous slides, that perhaps this expansion is not so surprising. So if you just take V and you evaluate it at epsilon f and you expand, you get this sum where you've got the nth power of divided by n factorial, and then you've got n many, y derivatives acting on V sub n. But now I've modified things a little bit. I didn't need that. I needed the y derivative of V and the x derivative of V. And so in my first term, I've got an extra 1 y derivative. And now in order n, again, it's one of these convolutions, I sum from 0 to n. And this gives me all the terms that are of order epsilon to the n. And then I also needed the x derivative. But also in the second term, I already have a power of f. I've got the d by dx f. And so in fact, in this convolution sum, I don't need to go all the way up to n. I only need to go up to n minus 1. So it's a funny thing. You never see, for the Neumann data, an appearance of n minus m. It's either plus 1 because you needed an extra y derivative, or it's minus 1 because you already had a power of f, which appeared in the definition of the operator that you cared about. So this is an added extra complication that we had to think about, but it's not that bad. Once you've recovered the a n p's, you need to do a second step to actually get the DNO with the method of field expansions. And what does it look like? Well, it's similar to what we did before. You take these known coefficients, you multiply by these particular powers of absolute value of q. We've got a convolution going on here in the wave numbers. And you convolve that with powers of f. And what's f prime? Well, it is actually a derivative of f sub m. It's d by dx f times f to the n minus 1 minus m divided by n minus 1 minus m factorial. This is our second one-line formula to produce the Dirichlet-Neumann operator. And so here is a MATLAB script which will produce not the DNO, but at least the field, these coefficients, these a n p's, written in MATLAB. And so you supply it with the Dirichlet data in what way? Well, you sample C, the Dirichlet data, at equally spaced grid points from, say, 0 to 2 pi, because we're going to do FFTs. We're using a Fourier spectral method. And then you supply me with F, the shape of the interface, but not pre-multiplied by epsilon. And if you want to compute for that particular interface G, you just evaluated epsilon is equal to 1. This is one of the beauties of these higher order perturbation of surfaces methods, is that if for some reason you care about some field quantity for all possible scalings of a particular shape, you just run this guy once, and by simply summing up the series for different values of epsilon with no extra work, you get the other quantities of interest for free. P is a vector of wave numbers. If you're in the business of doing Fourier spectral methods, you know that when you take the FFT of a vector, which represents a function at equally spaced grid points, that gives you approximations, highly accurate approximations, to the Fourier coefficients of that function. And what's returned to you? Well, it's the Fourier coefficients at wave number 0 to n over 2 minus 1. And then, from minus n over 2 to minus 1. It's just the way the computation is organized. And so P are these wave numbers. And they're in the right order. From 0 to n over 2 minus 1. And then from minus n over 2 to minus 1. Nx is the number of points that you sampled C and F, and is also the length of P. And capital N is the number of perturbation orders. And so the size of ANP needs to be what? Well, it's going to be a big array. Collection of vectors. And the way I've organized them is that you're going to have NX entries with columns and then n plus 1 many, or nx many rows, n plus 1 many columns. And now to do this computation, you need the powers of f divided by n factorial, and that's really half the subroutine. So the subroutine could be even shorter if I had as an input these fn's. And it's an easy thing to compute at perturbation order 0. This is the curse of MATLAB, is that you always have to start your indices at 1 rather than 0. So I always have a plus 1 in my index for many of my MATLAB codes. At order 0, well, after the 0 is just 1. So you return a column of 1s. And now to compute in a stable way these higher order powers, you just take, for f sub n, the realization that this is f times fn minus 1 divided by n. And that, in the end, will produce f to the n over n factorial. At order 0, what is the solution? Well, if you stare at my recursions here, you realize that when n is equal to 0, this whole sum here disappears. This just reflects the fact that if you just have a flat interface, obviously all that matters is the Dirichlet data of that flat interface, and those coefficients from the Rayleigh expansion are just the coefficients of the Dirichlet data. And then for higher orders, well, I initialize with zeros, and then I recursively add into the ANPs at order n, whatever you had before, and then these implement the corrections from order m multiplied by that operator absolute value p to the power n plus n minus m, and then that needs to be convolved with the powers of n. So the way I think of it is I am on the Fourier side, I multiply by these powers of absolute p, which are Fourier multipliers. I come back to the physical side, I multiply pointwise, not star, dot star, with the powers of n minus m, many of them, and then I come back to the Fourier side with the FFT. So that's how I do this convolution. This is a code to actually compute the DNO. It's very similar. And perhaps I should show a numerical result before we go on to the next method. What I did is the following. I picked out a profile, e to the cosine of x. So this is a nice profile because it's an analytic function. It's periodic with period 2 pi, and all of its derivatives have period 2 pi. And yet the function does not have a trivial Fourier series. It's not like the cosine of the sine. So it's got genuinely non-zero Fourier coefficients for all wave numbers p. And so if you work with spectral methods, you know that if you implement the derivative operator with a function that's got a finite Fourier expansion, then you notice that the error goes down very fast, and then all of a sudden it drops down to machine 0. So here at least, we don't have that phenomenon. And so what I did is I took, well, L is 2 pi, it's 2 pi periodic. The size of the interface is 2/100ths, not necessarily very big. A certain choice of numerical parameters, 64 grid points, 16 perturbation orders. And I computed these ANPs, or APNs, and then I computed an approximation to the Dirichlet-Neumann operator. And what I did is I picked out a solution to Laplace's equation, and there's a number of them. You can take the Rayleigh expansion and pick out one of those guys at wave number, say, r, evaluate it at this interface. That gives you Dirichlet data for which you can compute exactly what the Neumann data is. You just take the normal derivative of that function and evaluate it at the interface, and there you can compare the solution from your numerical scheme to an exact solution. And you notice the convergence of our scheme. And this is as a function of perturbation order n. And this is on a log linear scale. So you see the exponential convergence down to machine 0 times some sort of condition number for this problem. Okay. describe for you quickly the operator expansions method, which, as I said before, goes back to Milder and Craig and Soulin. And again, the whole method is based on the solution due to Rayleigh. But now, rather than working with the field, it works exclusively with the operator, hence operator expansions. Once again, we assume that the interface is shaped by G is equal to epsilon F, and that initially epsilon probably needs to be very small, although there are theorems that say that it doesn't have to be so. And now you just focus on this equation. The Dirichlet de Neumann operator takes Dirichlet data and produces for you this Neumann data. And how are we going to make progress? We are going to seek formulas for the action of G on a basis function. What's a good basis function for this Dirichlet data? Well, again, this is a periodic problem. The best basis functions are the complex exponentials. Let's try and find a formula for the action of G on this single complex exponential e to the IPx. And if we can do that, then we can find what the action is for any function C, because we just express it as a combination of these complex exponentials. As Walter mentioned yesterday, it's a linear operator in C. Let me consider this function, v sub p, e to the absolute value py, e to the IPx, which is one of the guys in this Rayleigh expansion, not by accident. This guy satisfies Laplace's equation, the relevant decay as y goes to minus infinity, and it's periodic. This is a good candidate solution for our problem. The only thing is, it doesn't satisfy the condition at the top. Let me take this guy and insert him into the definition of the Dirichlet de Neumann operator. Take this function. Dirichlet data is just this guy evaluated at y is equal to g. And then the Neumann data corresponding to this function is you take a y derivative and you take an x derivative and you combine them in this way. Now, let's assume, to get started, that the Dirichlet de Neumann operator does depend in a nice way upon epsilon, that it depends analytically upon epsilon, that you can make a Taylor series expansion of the Dirichlet de Neumann operator. And then let's expand everything else in that equation in powers of epsilon as well. What do you find? Well, Taylor series for the Dirichlet de Neumann operator. This is the Dirichlet data expanded. Oh, and there should be an epsilon to the m there. This is the expansion of the y derivative of f. It's the exact same, except you get an extra power of p, because you take an extra y derivative. Each of the y derivatives corresponds to a power of absolute value p. And now here's the second term, where you get n many y derivatives. But remember, you've got an extra d by dx f with an epsilon as well coming out front. This all looks very familiar. And in fact, it should. It's a slightly different approach to the exact same philosophy. Every time you see a y derivative, out comes a power absolute value p. And now you want to do the same thing. You want to collect up at each perturbation order what the relevant equations are. And it's unclear at the moment that you're going to be able to achieve your goal, which is a formula for g applied to each of the IPx's. Well, in fact, here's what we want, a formula for g sub n applied to each of the IPx's. And if we had that, then we could sum up that Taylor series and get an approximation to the action of the Dirichlet de Neumann operator on each of the IPx. Okay, well, let's start small. Let's start at perturbation order epsilon to the 0. Well, at epsilon equals 0, you only have this guy at order 0, this guy at order 0, this guy at order 0, and then this guy comes in at order 1. So he will not appear at order 0. And you find g sub 0, the only thing that remains at order 0 here is e to the IPx. At order 0 here, e to the IPx, but you do get a power of absolute value p. Right? This is good. We have formula for g acting on a single Fourier mode. And so what's the action of G on a generic 2-pi periodic function? Well, if you can expand it in a Fourier series, then you can write, see in terms of that Fourier series, G is presumably a nice operator, and you can bring it inside this infinite sum. And now we know what the action of G is on e to the IPX, at least at order 0 from our calculation. It's this absolute value P. This is a Fourier multiplier, precisely. So it was sort of suggested in the FE, field expansions methodology, that these sorts of operators play a role. It's sort of hidden a little bit, but you do see those powers P. Here it's absolutely explicit. Of course, this is what's going to give you, for water waves, water in infinite depth, for an infinitesimal surface, the dispersion relation. That's the absolute value of K that appears. So that's good. And you can imagine that evaluating this would be easy. You take your Dirichlet data, you move to the Fourier side by doing an FFT, you multiply by the diagonal operator in Fourier space, absolute value P, and then you come back from the inverse FFT. At order n, where n is bigger than 0, life gets a little bit more complicated. So what do you have? Well, in the leftmost equation, you had the product of two Taylor series, so it's going to be some sort of convolution, once again. And this is what it looks like. You can retain the DNO at order m, and then the Dirichlet data at order n minus m. And it's the same terms again. The powers of f to the n divided by n factorial, and then powers of absolute value p. And then the right-hand side is not so bad. You don't have these convolution terms. The first guy at order n gives you fn p to the n plus 1, because there was a y derivative. And now here, the second term does make a contribution in general. You have to keep in mind that there was an epsilon outside the front of that Taylor series. And so inside that sum, you need to take order n minus 1. And not only was there an x derivative, or a y derivative of order n minus 1, there's also an x derivative. So here's an IP, that's a classical derivative. Now here's the key realization. So the left is a bit of a mess, and it is not giving you formulas for the GMs applied to e to the IPX. However, when m is equal to n, these guys disappear, and you do get a formula for g sub n on e to the IPX. Take everything else and put it on the right-hand side, and if you have, you can think, if you have already computed the g sub m applied to these guys, then you have achieved your goal. You have a formula for g sub n acting on e to the IPX. And so if you take n is equal to this formula Walter showed us yesterday, if you take this guy with n is equal to 1 and n equals 2, then this will give you the formulas that Walter reported in his talk. This is a very elegant formula, but it's a bit problematic on a number of levels. One huge advantage, though, over the field expansions approach is that this is everything that you wanted, all in one formula. You don't need to solve for the field first, and then the DNO. This worked directly with the DNO right from the get-go. You can simplify things a little bit. So the Fourier multiplier, d to the m, absolutely d to the m, is defined by this equation right here. That's its action on a Fourier basis function. And so I rewrite these p's as d's. And now absolute value p squared is ip squared, and it's off by a minus sign. So you can deduce that absolute value d squared is minus d by dx squared, and you can actually combine the first two terms, these two guys. There's a product rule in there, because you differ, that's an n minus 1 and an n plus 1. There's a difference in the power of 2 in that derivative. Here. Here's my little product rule. And you see now that g sub n is equal to one term, which is a combination of those two in the normal derivative. And then you've got this big convolution sum. you write this all down, you get another one-line formula, and these are our slow OE recursions. I've already prejudiced you against these recursions. I'll explain why in just a moment. This was the formula acting on a single Fourier mode. And you just replaced e to the IPX's with x's, and now this works for every bit of 2π periodic Dirichlet data, which has a Fourier series. What's wrong with these recursions? To compute g sub n, you need to evaluate gn minus 1. That's fine. Why is that a particular problem? Here's the problem. It's gn minus 1 applied to this guy. Presumably, at the previous order, you have found gn minus 1, but it's only applied to xi, not xi pre-multiplied by these guys. How do you compute gm of these guys? Well, now you have to go back to the gm formula and recursively go back and do all this. And if you write it all down, you get very sad. And you decide that the cost of this is proportional to, well, at order little n, n factorial. The worst possible computational cost. Oh, well, this is a deal breaker. And in fact, in the paper of Catherine and Walter, they did not use all these formulas and create a code which could go to arbitrarily high order. They stopped after 4. They coded it up by hand. They did 0, 1, 2, 3, 4, and that's all they did. That's fine. We would like to be able to go to very high order. So there's 2 fixes. One of which is to say, okay, here's what we're going to do. This will be better than factorial cost. We're going to store at every order the action of g, not just on one basis function, but on all the basis functions in our computation. Okay, so we're going to pick out nx many grid points, which means you pick out nx many Fourier modes, and we're going to store as a matrix the action of this on all the Fourier modes that we care about. This is going to increase our storage, it's going to increase our cost, but it will be better than factorial. I believe I have it correct that your storage is going to be n times nx squared, and then the cost might have an extra log nx in this. It's not good, but it's not terrible. But there's a better way, and it's built upon the self-adjointness properties of the Dirichlet to Neumann operator. Life would be good if somehow we could take this guy and move him over to being directly applied to xi. However, you can't do this, because of course these don't commute. However, the DNO is self-adjoint, and all of the GNs are also self-adjoint. So take the adjoint of the entire equation. Of course, the beauty of the adjoint is that the adjoint of the product is the product of the adjoints with the order interchanged. Multiplication on the physical side, adjoint is itself, that is self-adjoint. The x derivatives, the classical ones, are skew adjoint, at least we understand them. And so you follow this whole path, and these give you the fast operator expansion recursions. Now it's a funny thing, you have to think a little bit. In the context of electromagnetics, you don't solve Laplace's equation, you solve the Helmholtz equation. Not self-adjoint. However, you can solve an adjointized version, which will give you a slow method for the wrong problem, which, when you take the adjoint, gives you a fast method for the problem that you care about. It requires a little thought. And so here's a code to do operator expansions. I'm running a little bit low on time. But it's the same sort of philosophy as before. You supply xi and f and this vector of wave numbers. This could also, you could drop that and then just do in line number 1 what p is, and x and n. You set up the powers of f, and now what are you going to return? The gn's, which are to be compared with the anp's. It probably should have been gnp. It's got the same dimensions. For every perturbation order n, you need a vector of length nx. And now I'm going to compute the FFT of xi. Do I need the x derivative of xi? I compute it. I don't know quite why I need it. Never mind. order 0. Maybe extra, see?
3 lines down, you use it.
I can get away without it. Never mind. That gives you the DNO at order 0. So it's C hat, C FFT, absolute value P, and then bring it back, diagonal operator. And then here are all the corrections to compute the GN. So at each perturbation order, you start with, remember, these were the 2 terms that I combined. And then these are from the fast OE. You can reuse your computations. The important thing is that now G is applied to C directly. That you have already computed. You've pre-stored that. You multiply by power of F, and then this Fourier multiplier, and that's this. This guy you pre-computed, he's on the physical side. You multiply pointwise, take him to the Fourier side, multiply by this operator, pointwise, it's a diagonal operator, and then come back to the physical side. And now, as I explained before, you can do numerical tests based on exact solutions. Here was FE, and here was OE. And so despite the fact that we're very worried about the derivation, this seems to be giving good results when epsilon is small. Hidden in the whole derivation of the operator expansions method is the fact that you use these solutions, which are only solutions away from the boundary, and you recklessly evaluated them at the interface.
But there's also a philosophical point. The philosophical point is that, in principle, the Neumann map should have nothing to do with the solution inside. You see, you shouldn't have to go back to solve Laplace problems again and again. I mean, you should be able to stay only the boundary. This is the essence, the beauty, the power, whatever you want to call it, of the Neumann. As you, of course, you know what we did on this with algorithms. But again, we didn't do any serious numerical effort. So my point is just philosophical, but I think it should be raised.
But the engineers have been doing this for a long time, and it gives some good results. The comparison, you can't see the difference. And maybe I'll stop here for today, but I'll come back to next time these problems, which you worry about because you've evaluated things at the interface and taken this particular philosophy of perturbing about some geometry that you understand very well. And that's the point. On this flat interface geometry, you know what the solutions are. They're very easy to compute. And so wouldn't it be great if you were just a small ways away from it, and you perturb from that? And that's a great idea, but it can be a bit problematic. And so maybe next time I'll start up with, isn't it easy to do 3 dimensions based on this, and then finite depth, and then talk a bit more about how you can fix some of the shortcomings of these algorithms. Ben will speak on this tomorrow, and I'll come back and talk to you again on Thursday, and then Ben will conclude on Friday. Thank you. Yes.
Have you ever calculated this for any realistic flow? Not that kind of a flow, but like flow over a wavy surface or the undulating surface, by some kind of a forcing or wind over waves or anything that can actually be used in oceanography.
I think I have.
You have any
But I don't know if you will think that I have. So here's what I've done with these things. I've computed families of traveling water waves using this algorithm, and it's worked out very well. I think Goyen perhaps has tried to do more demanding, more realistic simulations with this method than I have. Walter and Catherine were attempting to do things along these lines, but as soon as you start making the initial model, potential flow with just these effects, gravity, surface tension, now you need to start adding in more realistic things. Now you need to add in all the different forcings, and I think in theory, it's going to be fine. But then as a practical matter, here's one thing that we can't accommodate at the moment with this formulation. You cannot do overturning.
Oh, yeah, well, yeah, that's a different problem.
You can imagine, though, maybe, an overturning wave is a big perturbation of flat. That might be well outside. This is another question. I sort of skipped over it. How big can epsilon be?
How how big do you think it can be?
So here's the theorem. You can prove that these expansions converge, provided that F is sufficiently smooth for a small disk in the complex plane of epsilons. At times it can be surprising how big it is and how small it is. However, you can also show that the domain of analyticity includes the entire real axis in epsilon, provided you're in deep water. As soon as you put depth in there, then, well, it's limited. You can't have cavitation. And so the question becomes, well, this is good. Inside the disk of analyticity, I'm just going to sum up the Taylor series, because that will converge. How do I get to points that are outside the disk, but that are still inside the domain of analyticity? And so what we've done is we've done Pade approximation, which is an attempt at numerical analytic continuation, which has all sorts of magical and mystical powers, which are not well explained. But we found it to be a very powerful add-on to our method that allows you to do very large deformations. And we've also done a bit of study, okay? There are no singularities in the expansion on the real axis. Where are the singularities? Well, we find that they usually cluster on the imaginary axis. Well, they're all over the place. Where the important thing is, where's the smallest one in magnitude? It appears to be on the imaginary axis. But now how can you use that to your advantage? Is there some way to use that information to expand the domain of analyticity or to create a better designed summation technique to take advantage of this? So that's how we've done very large deformations, is with Pade approximation. But again, once you start having extreme geometries with nasty corners and so forth, it gets hard.
But it's, in what you described, the whole code still stays stable.
If you start making epsilon large, if you start pushing the number of perturbation orders larger, I'll show this on Thursday, then some of the results become a little bit less predictable. One goal of this is, not necessarily to do the most extreme configuration you can imagine, but someone who's more of a PE specialist has a question about how solitary waves interact. And we give them a very short MATLAB script. They can provide initial data, just set it running, and it will produce reliable results for them. That will be something that's nice. And then maybe in the same package, someone's integral equation solver is also there. Compare the two.
The separation of variables you can also do in a closed domain. You just don't get e to the I pay dx or something else. So you would think it would work there. Is that correct?
That's right.
So you did that. Because I mean,
That's
the
correct.
idea should
Yeah.
work, right?
Yeah, that's
It
right.
shouldn't be too horrible.
That's right.
Instead of i's, you have something else. You have the decaying exponential.
So yeah, I think the idea is a powerful one, and there's many avenues that you can pursue from here. Yes?
So in engineering, when you want to calculate wave forces and stuff like that, you often use Stokes fifth order waves or string function waves, steady propagating waves. I guess this would be one of the most obvious ways to try to reconstruct with this new method. Have you
So in fact, if you
done that?
take, right, so we only talked about the boundary value problem today, and then we'll talk a bit more tomorrow about the specifics of water waves. If you take this philosophy and apply it to the full water wave problem, you recover the classical calculation of Stokes. You'll recover at order zero, is order zero solution, and then you'll go through and you'll get all these different order approximations. You will find that fifth order approximation. Something. So this is just making that procedure, putting it in our language, and it's taking it to very high order, and then it's putting it on a computer. And you have these coefficients, which are going to be indexed by perturbation order, and then P, which is the number of modes that you retain. And now that expansion, so the beauty of the field expansions method is that now you don't recover just the field at the interface, you can evaluate that anywhere. So the analog for water waves allows you to find the velocity potential not only at the free surface, but also inside the fluid. You can take the derivative and you can find velocities inside the fluid. I mean, it's an old idea, and it just seems that people haven't taken it to very, very high orders before, for a number of reasons. And the H in HOPS is important to us. There are problems where it's not so important that you go out to order 16, but there are some.
Can I ask you a question about aliasing? Is aliasing not a problem? I mean,
It is a problem.
so you haven't taken
It's
care
not
of.
the worst problem. It's not
Well,
the worst problem.
I don't know.
It exacerbates the worst problem.
Yeah, yeah.
That's
So
right.
that's why you. But why are you choosing 64 and not 32?
Oh, you could take a 32 if you want to.
Yeah.
It depends on the profile. Yeah, and that's part of the goal with the coats. You take the coats home, you run it with 32, you run it with 16, you run it with 8, you run it with 1024.
But of course you don't know what the non-linearity is. Yeah, I mean for quadratic non-linearity it's 2. The ratio between nx and n. But for cubic it will be more.
You mean in
The more non-linear it becomes, the more problems you get with aliasing, and you have to resolve in spatial domain.
yeah, and this was one thing that was in Walter and Katzmann's paper, is they had to do extensive filtering using this method when they simulated water waves. And Victor was talking yesterday about how difficult it is to simulate water waves. And then, this is something that's typically nice about these integral equation methods, is that they do a better job, I think, of being more stable than perhaps our approaches are. And there's various ideas for adding in filtering to our methods. And one thing that we've explored a little bit is adding in a little bit of dissipation. Is there a good way of adding this in a physical way that can help solve some of these problems? So yeah, aliasing is a problem, but it makes a different problem worse.
Okay, let's thank Dave again.
So make sure you come back at 11 to listen to these bombs. We're very Panasis is going to talk about